So this first set of questions comes from the theorems that we talked about yesterday. If we have a tangent line, and it says assume that this is tangent, so it tells you in instructions to assume this is a tangent line, and you have a radius or a diameter, because the diameter is just the radius doubled, that touches that line, you know that it is perpendicular. So this information automatically tells us that we have a right angle right there. Which means if I'm trying to solve for a side in a right triangle, I can use the Pythagorean theorem. Biggest problem I see with Pythagorean theorem is just setting it up wrong. Make sure that your C is always the hypotenuse. So in this case, you should have said 6.8 squared plus the one that I don't know, squared, equals 17 squared. So when you solved that one, you should have gotten 10.2. All right. The second one was identical. They actually gave you the hypotenuse in this one as well. And so you would have set that up exactly the same. You would have said 5.5 squared plus the side I do not know squared equals 14.6 squared. When you subtracted and took the square root, you would have gotten 9.6. The other issue I see here is getting ready to solve it and not taking the square root. And so make sure when you get to the end, you take the square root as your last step, because you're solving for something squared. So make sure you take the square root when you get to that point. Again, it tells you if it looks like a tangent, then assume that it is. They want you to solve for x here. This is the theorem that said if you have two tangents that go to the same point outside the circle, then those tangents are going to be congruent. And so for this one, you're literally just setting those tangents equal to each other and solving. So for this first one, you have x plus 16, and you have 3x minus 4 are your tangents. You know these are congruent based on that theorem, so you can just do this. And then you're doing basic solving. Variables on one side, numbers on the other. And so once you do that, you're going to have 20 equals 2x. Divide both sides by 2. X here should be 10. Do exactly the same thing on the other side. You don't even need the 24.4. That's additional information. You can set 4x minus 3 equal to 2x plus 15. Variables on one side, numbers on the other. Cancels here, you get 2x equals 18, so x here equals 9. The same exact concept, knowing that your tangents are equal. How do I find my perimeter? If I know this is 7.3, then the tangent that leads to that same point there is also 7.3. If I know this one is 9.9, then I know this one is 9.9. I know this guy is 8.8, which helps me figure out this one because it leaves the rest of this. 20.8 minus 8.8 gives me 12. So that tells me that this one right here is also 12. And then you just add them up. You just add the 12 and the 7.3, 7.3, 9.9, 9.9, 8.8, and the 20.8. And you should have gotten 76, I believe is the answer for this one. For the second one, you would do exactly the same process. If this is 10.9, that's 10.9. This is 13. To figure out this side, you're going to take that 9.8 and subtract it from the 20.7, which is going to give you, what, 10.9? Something like that. Add it all up, you should have gotten 89.2 for this one. We're going to look at arcs, and arcs are pieces of your circle. So we looked at sectors in the last chapter, which is like the pie. So if you had a piece of pizza, that's a sector, and that whole piece of pizza is the sector itself. An arc would be like just the crust, all right? It would just be the part that goes around the outside. And so the arc is created by a piece of the circle itself, the circle's perimeter, not the inside of the circle. And so when we talk about arcs, that is just the perimeter of the circle or the circumference of the circle that you're taking a piece of. There are different types of arcs. The first type that we look at here is a semicircle, which I'm sure you've heard this term for. It is half of the circle. And so a semicircle example would be from W to Z to Y. That would be considered a semicircle there, a semicircle. It is half the circle. And because the circle is 360 degrees, the semicircle is 180 degrees. A minor arc. A minor arc is an arc that is less than 180 degrees. So a minor arc is less than 180 degrees. An example here would be from W to X, from W to X. That would be a minor arc there. And then a major arc. A major arc is more than 180 degrees. And it is going to have sometimes the same, or always the same endpoints as a minor arc. So if I were going to give you a major arc, I could say, well, I'm going to go this direction, W to Z to X to Y to X. So you'll notice it has the same starting and ending point as my minor, W to X. And so then you run into the situation, how do I know which one I am talking about? And so you want to label these with the correct number of variables or terms, okay? And so first of all, let's look at notation for arcs. If I want to do a notation for an arc that is anything other than a major arc, I am going to use 3 capital letters. If I am doing a minor arc, I'm going to use 2 capital letters, all right? So if I wanted to do this minor arc W to X, I would just list W to X, and then the notation is actually a little arc above it. That means the arc W to X. But let's say I wanted to do the major arc W to X. All right, the major arc W to X is still going to have a starting and end point of W to X, but I need to include one of the letters that goes on in between it. Either one is fine. So I could say WZX or WYX, but I'm going to list 3 of them with that arc over it. All right, so these two have the same starting and ending point, but one is a minor arc, less than 180. One is a major arc, greater than 180. If I wanted to list that semicircle, I would list 3 as well, because I need to know which side of the semicircle I'm talking about. So if I wanted to list the side that I highlighted there, WZ to Y, that would be that semicircle. WX to Y would be the other half on this side. All right, so if I look at this theorem, the measure of an arc formed by the union of 2 adjacent arcs is the sum of the measure of the 2 adjacent arcs. This is the arc addition postulate. This should remind you of the angle addition postulate. Remember, when you have 2 adjacent angles, you can add the 2 angles and it makes the whole. Okay, it's the same thing with an arc. If you have adjacent arcs, you can add the 2 and it makes the measurement of the whole arc. So look at example 1 there. Find the measure of each arc in the circle V. If the measure of Y to Z is 45 and the measure of WVX is 60 degrees. WVX is 60 degrees, all right? Now, some things here about arcs. The measurement of the central angle that makes it is going to be the same as the arc itself, okay? Arc measure is talking about the angle that makes it up. We're going to talk about arc length next, but arc measure is the degrees or the angle that makes it up. So if they told me that Y to Z was 45 degrees, then I know that the angle that makes up that arc is also 45 degrees, even if it doesn't look like it, all right? 45 degrees. They told me that W to V to X, W to V to X is 60 degrees. So this angle is 60 degrees, which means this arc is also 60 degrees. So the arc measure is the same as the angle that makes it up. And now they want me to find some other things. All right, so I have 60 and 45. 60 and 45. They want me to find Z to W to y, all right? From z to w to y. So if I go from z to w all the way around to y, I have the entire circle except what?
The 45.
Except the 45. So to solve for this one, I'm going to just take the 360 minus the 45. So this angle measure is going to be 315 degrees. Easy enough? All right, let's look at the next one. They want me to do y to x to w. Y to x to w. All right, so I'm now going to look at, let me get rid of this one here. We're going to look from y to x to w. All right. Now I'm missing a piece of this, but what can I tell about from y to x to w? It's half of a circle, is it not? Do I even have to measure it? No, I don't have to do any calculation. What is half of a circle? Always 180 degrees. All right. The next one they want is z to w. They want from z to w. I'm missing something there too, right? I don't have that, but it is part of this guy right here. So this whole entire one right here is a half a circle, right? So if I know this whole thing is 180 and I want all but this piece, I can just subtract. All right, so if I know it's part of a half a circle, all but this 45, I can just say 180 minus the 45. All right? So I have, this is 135, right? How do I find this last piece here? Z to x. I need to know this piece of it to go from z to x. I know all but that one piece. So from y around to w is 180. I know this piece is 60. So to find this leftover, I can say 360 minus that, right? Or I can say 360 if I'm trying to find from z to x. I can say 360 just minus these two pieces. So there's a couple ways to solve this. 360 minus the 135 plus the 60. Either way, you should get 165 for this one. All right? So you're basically just looking almost like a pie chart. And you're saying, what pieces do I have? What pieces do I want? All right? Endpoints are A to D, and it goes through E. From A to E to D is a minor arc, so all you had to do was include the A and the D with the arc symbol and tell me that it was a minor arc. All right. The endpoints were E and C, but they wanted you to go through B. So to go from E through B all the way to C was a major arc, so you actually needed to include 3 letters with that arc symbol and tell me it was a major arc. A major arc. Endpoints are A and C, and it contains B. A through B to C, that is actually a semicircle, so you needed all 3 of those. And list 3 points. It says, do not confuse arc measure and arc length. Arc measure is the angle that makes it up. So you can think about it the rotational measure, okay? So how much did you rotate to create that arc, all right? Arc length is different. Arc length is as if you were going to take that string that goes around the circle and stretch it out and actually measure it, okay? And so this depends on how big the circle is. You can see the example that they give you here. We have this circle that's on the inside and this circle that is on the outside. The arc measure from E to D is actually the same arc measure as A to B, because it is the same angle that made those up, right? The same angle that made up this A to B also made up this D to E. Those were created by the same angle. So the angle measure or the arc measure is going to be the same. Let's say it's 60 degrees. So the arc measure of AB is 60 degrees. The arc measure of DE is 60 degrees. However, it's obvious that if I were to cut those pieces out of the circle and lay them flat, ED would be longer than AB. Why? Because the radius of the outer circle is bigger. And so that is arc length. Arc length is how long that piece of the circumference is. And it is dependent on two things: the angle that makes it up, as well as the radius that created it for that circle. And so that is where we get that theorem that is listed below it. If an arc of a circle with a radius r and circumference of 2 pi r has a degree measure of theta, theta is a Greek symbol, it's just like a variable, then the arc length is given by theta over 360 times the circumference, all right? What is that telling me? It's saying, okay, I'm going to start with the circumference of a circle. 2 pi r, that is my circumference, all right? That is how long the entire circle would be if I were to take the string and stretch it out, right? That's 2 pi r. But I just want a piece of it, so I have to know what percentage of it I have, okay? And so to find the percentage, I'm going to do just like I did with sector. I'm going to say, well, the angle that makes it up over 360 is the percent of the circle that I have, okay? So if I'm trying to find the length of that arc, I want to take the percentage of the circle that I have, which is the angle over 360, and I want to multiply it by the circumference, 2 pi r. And that will tell me how much or how long that arc is if I were to stretch it out. All right, so let's look at these examples here. Look at example 2. Find the value of each variable. Find the value of each variable. What is my angle measure for A? What is my angle measure right here? And how do I know? Yeah, it gives me a box there, which tells me it's a right angle, which is what degrees? 90. So I have 90 degrees out of 360 degrees, okay? And then I need circumference. How do I find the circumference of this circle right here? 2 times pi times what is my radius? 10, right? And so if you want it in decimal, you would plug that into a calculator. If they want it in pi, you're going to reduce it. 90 out of 360 is 1/4 times 20 pi. We are going to cancel our 4 and our 20, 5 pi. That is exact. Rounded means put it into a calculator. 15.7. They are both yards. It is not yards squared. I am not talking about area. I'm talking about length, okay? If it was area of the sector, it would be squared. It would be a square units. Length is just the units, one-dimensional. All right? They can also go the other direction. What did they do for this next one? They gave me the length of the arc, okay? So for B, they gave me the length of the arc. I know that the length of my arc is 5 pi. What I don't know is my angle. So I don't know my angle, but I know it is out of 360. And I do know my radius. So I know that's going to be 2 times pi times 15. Right. And so now I'm going to solve this one. And you can simplify it. Remember, we're solving for that variable there. 2 times 15 gives me 30 pi, right? And then I can reduce 30 and 360. How do those cancel? My zeros cancel. 3 goes into 360 how many times? 12, right? So I have 5 pi here. Here I have theta times pi over 12. How do I solve for theta? Think of it as 5 pi times theta, or equals theta over 12. We'll do pi over 12, actually. We'll just do theta times pi over 12. This is a fraction. How do I get rid of that fraction? Multiply by the reciprocal. Yes, 12 over pi times 12 over pi. What cancels here? What cancels? My pi cancels. 5 times 12 is 360, that is my theta. This is a 60-degree angle. So you're just working backwards, okay? They've given you the length and you're working back into it. They've given you the length and you're working back into it. All right? Make sense there? A little bit more work. What about this last one? C. All right? I know part of it, 330. How does that help me? What's my theta here if the rest of the circle is 330? What's an entire circle? Right, 360 minus 30. So my theta here is 30. Again, they've given me my length, but now I just need to know radius. So my length is 4. I know that I have 30 over 360. I need 2 times pi times my radius is what I'm trying to solve for. Same thing here. We can cancel out my 2 and my 360, right? We can reduce the 30 and the 180. You're doing a lot of fraction work here, so make sure you know how to do fractions. So 4 equals, this reduces to 1/6 pi times r. So multiply by 6, divide by pi. We get 24 over pi is my r. Put it into your calculator if they want decimals, 7.6, and we are in feet is my radius there. All right, so go back to page 365. For this one, congruent arcs or arcs on the congruent circles are the same circle and have the same measure. All right? In order for them to be congruent, you have to have the angle that makes them up congruent as well as a congruent radius. Okay, as well as a congruent radius. All right. The next theorem is on the following page, or actually right below it. Incongruent circles, minor arcs are congruent if and only if the corresponding central angles are congruent. So all it's telling you is the only way you can have a congruent arc is if both things add up. This one is made of the same central angle, and your circles are congruent, meaning they have the same radius. Chords of congruent circles are congruent if and only if they intercept congruent arcs. So we talked about congruent chords being the same distance away from the circle. So if these chords are congruent, then the arcs that they intercept are also congruent. The arcs that they intercept are also congruent, which is basically what those theorems below tell you. Incongruent circles, chords are congruent if the central angles are congruent. Incongruent circles, minor arcs are congruent if the corresponding major arcs are congruent. The pieces have to be congruent.